Hi everyone, welcome. Thanks so much for joining us today. I'm Claire from Keep Northern Ireland Beautiful, and I'm the coordinator of our Tackling Plastic NI project. This project is funded by the Department of Agriculture, Environment and Rural Affairs. This is the 7th in our series of short webinars for Tackling Plastic for Eco Schools NI, which is run by Keep Northern Ireland Beautiful. And today I'm delighted to have Professor Tom Welton from Imperial College London with us, who is going to delve into chemistry and sustainable plastics. Solving the problem of plastics in the environment requires action by both the public and the industry, and Professor Welton will explore some of these actions with us today. So by the end of the webinar, we hope you'll all feel empowered to take eco-action to reduce your use of pointless plastic in school and at home. And before I hand over to Professor Welton, I'd just like to introduce my colleague and co-host, Francesca.
Hi, everyone. Thank you, Claire. Thanks to everyone for joining this webinar today. My name is Francesca. I'm the Eco Schools and Wiry Project Officer for Keep Northern Ireland Beautiful. And today I'll be moderating this chat. So please use the chat for any comment you have. And then if you have any question for Tom, use the chat box, the Q&A, box that is right beside the participants at the bottom bar. And then any other link will be added in the chat during this webinar. So over to you, Tom.
Thank you very much, Francesca, and thank you, Claire, and thank you for the invitation to speak to you today. So I now need to share my screen, which will just take me a moment. There we go, and you should now have the first slide. So what you'll see on this slide is there's a little A star in the top right-hand corner. And if you see that A star as we go through the talk, what that means is the thing that's on that slide is relevant to what some of you will be doing in your A-level syllabus. And so it will connect in with the things that you're in this year, next year. It'll connect in with what you're learning as A-level. And so today, I'm going to talk to you a little bit about both of what Claire said, a little bit about what you can do in order to take us to a more sustainable plastics future, and then a little bit about what industry does with your plastics, you'll see as we're recycling or whatever. So for me, this story really begins with this woman here. This is a Norwegian politician, Gro Brundtland, who led the UN World Commission on Environment and Development. And in 1987, they released this report, Our Common Futures. And it was really the first time that sustainable development became defined as an idea. And, you know, you can't reduce a 600-page report down to one sentence, but nonetheless, I've done so. And what it really gave us was this idea that sustainable development is development that meets the needs of the present generation without compromising the ability of future generations to meet their needs. And you can see it's a very simple and elegant idea. And then sustainable chemistry, which is the thing that I do, is really quite simple because you can just relate it back to that. And so it becomes the implementation of the concept of sustainability in the production and use of chemicals. So that's how do we operate as a chemicals industry? How do we operate as users of chemicals? And very much that's really the kinds of things that I will be talking about today. And for those of you that have had this in class so far, it pretty much is a reasonable summary of the idea of green chemistry. And then there's an important and the and is that the application of chemistry and chemical products can enable sustainable development to happen. So what can we do to help chemistry contribute to sustainable development? So much more positive idea there, really. But what I want to first mention about is, and I love this quote by Niels Bohr, and it's that thing about not compromising the needs of future generations. And what Niels Bohr said is prediction is very difficult, especially if it's about the future. So let's go into the past. So this is a photograph taken in St. Mark's Square in Vatican City in 2005 at night. This picture was taken at pretty much the same place 8 years later in 2013. And I think if I toggle between the two of them, it's pretty clear what the difference is. As in 2013, suddenly we can see the bright lights of all of our telephone screens, our iPad you can see in front of you. And what we're actually seeing, of course, is the screen. And I'd like to talk to you about that for a minute or two. So here are the elements that you can find in a smartphone. And the first thing you can see is there's a lot of them. There are over 30 different elements that you can find inside your smartphone that you have in your pocket just now. And a whole range of them. You know, so some which are, you know, very abundant. We'll see that in a moment. Things like oxygen and carbon, of course, is in there. But then you can see all sorts of elements that perhaps you might not be so familiar with. I mean, I don't know if you've ever heard of europium or dysprosium, these rare earth elements that can be found in things like the batteries or producing some of the colours that you get on your screen. But what I'd really like to focus on today are these three. And this is indium, tin, and oxygen, and together they make a material that's called indium tin oxide. And indium tin oxide is a remarkable material. It's transparent, so you can see through it, and it conducts electricity. So what that means is, of course, the transparency means it can be a screen. You need your screen to be see-through. But the conductivity means that when you touch it with your finger, an electrical current can pass that operates the screen. And so your swipey screen is this indium tin oxide material. Now here we have a periodic table. And it's probably quite unlike any periodic table that you've seen before, but trust me, it is the same. And this periodic table was produced in 2019, the International Year of the Periodic Table, by the European Chemical Society. And what it represents is not just what the elements are and the chemical relationship between them that you see in the normal periodic table shape, but it's showing you the abundance of the different elements. And the size of the element symbol tells you how abundant that element is in the Earth's crust. And the bigger the symbol, the more there is. But actually, you have to be a little bit careful because it's on a logarithmic scale. So twice the size, in fact, means 10 times the amount. Otherwise, all you would see is a huge, great oxygen, silicon, and hydrogen, and you'd see nothing else at all. So we have the amount of the element that there is. But then there's a color code, and the color code tells you about how that amount relates to how much of this element we use. And so if it's green, what that means is there's a completely plentiful supply. And no matter what we think we're going to do, we seriously doubt we are ever going to run out of oxygen. There's so much of it. And then we start seeing the other colors. And so we have yellow. And what yellow means is, do you know what? Given that we do use this element quite a bit, then there may be some future risk to its availability. And you can see here things that are still quite common elements like phosphorus and magnesium. Then we start getting the orange ones, the amber ones, which are, there's a rising threat from increased use of this element. So this element is becoming much more commonly used, and it's not necessarily so abundant. And so you see things like ruthenium and rhodium, palladium and platinum, the kinds of materials the types of elements that you might find in the catalytic converter of your car. And then there are the red elements. And so the red elements have serious short-term threat to their availability for us to use in the way that we use them today. And what that means by short term, it means sometime over the next 100 years, we could run out of that element. And if you look down here, there it is, indium, an element at serious risk. And so what's happened is, since 2005, when we didn't have swipey screens, to now, well, and indeed by 2013, just 8 years later, indium has gone from being an element that no one really cared about. Some of us chemists loved it because it had interesting properties, but in terms of our day-to-day lives, indium didn't really impact very much on our day-to-day lives. Whereas today, would any of you want to take your mobile phone and smash it on the ground and say, I'm never going to use that again? No, of course not. And so indium is now a vital element for how we live our lives. Whereas just a few years ago, as I said, it wasn't. So if something can change so quickly from being insignificant to vital, and as it turns out, from being what would then have been hugely abundant to under serious threat in just a few years, we do have to ask ourselves, how do we predict the future? How do we predict that our successors might need this in 50 or 500 years' time? I don't have any answer to that question, but it is a problem that we have. And so what we tend to do now when we think about sustainable development and sustainable chemistry is to think about it in terms of these, which are the Sustainable Development Goals. And you can see what they are. I shan't read them all out, but from no poverty and zero hunger and good health and well-being, to reduced inequalities, peace and justice, responsible consumption and production. We're going to talk a lot about responsible consumption today. And you can see that there's this huge variety of 17 goals. And for me, sustainable development is now really saying, how does chemistry contribute to achieving these 17 goals? And what I recommend that you do is that actually, not now, but later on, you find these again and you think for yourselves, what do you think chemistry can do to help us achieve all of these goals? Because I think chemistry and chemists certainly have a role to play in all of these goals. So in doing that, we do still need to remember the first thing I said about the implementation of sustainable ideas in chemistry itself. We do need to try and achieve the Sustainable Development Goals, and in so doing, we need to use less stuff. So we need to consume nature's resources at a rate that is lower than that at which they can be naturally replenished. So we won't be using stuff up. We won't be destroying stuff forever. And we need to make less waste. So we need to produce waste at a rate at which it can be naturally remediated, or less than that at which it can be naturally remediated. And if we can do that, together with using less stuff and achieving the Sustainable Development Goals, we will then have developed a truly sustainable chemistry. But today I'm going to focus on the issue of plastics. And, you know, plastics have come to the fore very recently in the public's eye, really, you know, and I think you can almost, it's one of those few things that you can perhaps fix down on a, you know, a particular moment, or I should say a particular television program, The Blue Planet. And what happened with The Blue Planet was we started to see on our screens this problem that plastics are genuinely everywhere in our environment, and particularly in The Blue Planet, in our seas. And we started to see images like this, not only of the presence of plastics, but the terrible damage that they can cause. And plastics are genuinely everywhere. And so what I'm showing you here is a map of the South Pacific Ocean, and, you know, a tiny little dot of an island in the middle of the South Pacific where the marker is. So small, you can't even see it on the map itself. And that island is called Henderson Island. It's one of the Pitcairn Islands. And in 2017, a group of people went to the island to study its beaches. And that's what you can see on the right-hand side. Those are pictures of the beaches of Pitcairn Island. Now, these are not islands that have a huge tourist industry. You know, if you turned the camera around on that picture, you wouldn't be seeing a hotel. What you would see is just an island. And so, in spite of the fact that this island is pretty much as far away from anywhere of major human habitation as you could possibly get, its beaches are covered in plastics. And in fact, what they found was nearly 38 million items weighing almost 18 tons on the beaches of Henderson Island. And that was at a density of nearly 350 items per square meter. That's a huge amount of plastic that has found itself on Henderson Island. So plastics are everywhere. But then think about why. Why are plastics everywhere? And the reason is that we use so much of them. And so the pie chart here is representing the amount of chemical products that are produced by an oil refinery and the successor industries of the oil refinery that are not fuel. So we've put the fuel to one side, we're not counting that. That's the vast majority of the mass of material that a petrochemical refinery produces, but the rest of its production goes to the kind of things that we find around us in our homes and, you know, out in the streets, etc. And what you can see here is that nearly 80% of the mass of material that we make in the petrochemicals industries becomes plastics. That's huge. That is, of course, plastics are everywhere because they are everywhere. We use them everywhere. And, you know, and as I look around my home and I think, you know, what would happen if I took all of the plastics out of this room? You know, okay, there's quite a bit of wood, but apart from that, there would not be much left. And so plastics are everywhere because we use plastics everywhere. They are a kind of ubiquitous set of materials. And here is a graph showing a prediction, but also a picture showing a summary of what's happened to all of the plastics that have ever been made. And so the estimate is that around 8.3 billion metric tons of plastics have been made ever since we started making plastics. Now, of those, 2.5 billion metric tons are still in use. And that's one of the things that we have to remember about plastic. So we do think about plastics as throwaway things, as, you know, packaging, cheap items, pens, that kind of thing that get used and then very rapidly disposed of. But many plastics are in uses where they are used for long times. And so this morning, because I knew I was giving this talk, I had a little bit of a route around and thought, what's the oldest bit of plastic that I've got in my kitchen? And it turns out that, you know, inside one of the drawers, I've got, you know, as people do, I've got one of those cutlery, tidy tray things. And that piece of plastic is now over 30 years old. And so it remains in primary use. You know, and that shows just what a durable material plastic can be. But, you know, what's happened to the plastics that aren't currently still in use? And what you can see here is the blue arrow, and that shows you how much plastic has been recycled after that primary use. And it's roughly 600 billion tons have been recycled. So that's a tiny fraction. It's less than 10% of the plastics that have been made have ever been recycled. And what you can see is that nearly 5 billion metric tons, so the vast majority, has been discarded, either into just dumped or into landfill. A small amount has been incinerated in order to recover the energy of it. And what you can see on the graph are the terrible predictions for the amount of waste that we will generate over the next 30 years if we don't do something about this. And it's staggering. So what can we do about this? Right, and so here, and you may have heard of sometimes I've heard even the 3, the 4. I'm just going to talk about the 5, and in fact add a 6th later on. The 5 R's of how we can think about plastics. And so this is about what you can do. And so the first thing that you can do is you can refuse. You can say, that is a pointless plastic and I am not going to use it. And the example I've got here is of balloons, which are very happy, joyous things. Here we see a release of the balloons at probably a charity event or something like that. But then we see the consequence of that release. And with balloons, we really are. So one, the balloons tend to be filled with helium, which is itself a precious natural resource and an element that is at risk. There are plastics of the balloons, which then get distributed around the countryside in a completely random manner, where they snag in a tree or get caught in something, and eventually they just fall into the environment, creating the litter that you see here. And so you can ask yourself, is the picture on the left-hand side worth the picture on the right-hand side? Of course, there are other things, plastic straws have very much come to people's attention. But I would say straws in general. I was in a bar. I'm 56, so that's okay. I was in a bar recently where I was given a drink in a glass with 2 straws in the glass. And one, it was in a glass. I could have quite happily just drunk from the glass. If I had been so desperate for a straw, I could have used just 1 straw. And so this complete wastefulness that was utterly unnecessary, we can refuse. I did. I told them to take the straws back. Not that that would have changed anything there, but maybe it would have made them think next time. And there are many things, if we think about them, that actually we can just refuse. We can say, I am not going to use that type of plastic, or maybe even that type of thing ever again. And then the second of the R's is to reduce. And that means this. I mean, here's an example of, this is a collaboration, if you like, between the manufacturers and us, the consumers, the people that are buying the products. And, not long ago, maybe 10, 20 years ago, when liquid detergents first came around, we would buy massive 5-litre bottles and lug them home to do our washing, whereas now we do that with detergents in much smaller bottles. but still give the same amount of washing power as the previous bottle did. And that means that there is less packaging. Less packaging means less plastic. There are also other advantages to this. So the main thing that got removed was water. And so a lot of money and energy was spent driving water around the country from the suppliers to the shops. And so by having a smaller bottle, not only does it use less plastic, in fact, it uses less fuel to transport it to the shops. And so there's a double success there. Here in the middle, you can see another example where fortunately the manufacturer has told us how much less plastic we're using. And so, you know, you buy the original liquid soap in its plastic bottle with its plastic dispenser, which will also have metal parts in. And then you don't need to buy another one of those bottles. When it runs out, what you can do is buy a refill pack, and you can see this refill pack has 75% less plastic than the original. And so therefore you end up reducing your use of plastics. Then there is reuse. So reuse means using the thing for its original purpose again. And so the example that I've got here is, you know, the replacement that has happened of supermarket throwaway carrier bags with stronger bags for life, and or whatever it is that they get called at your local supermarket, that you can reuse again and again and again. And so ultimately you use less plastic because you're reusing the product. Another example I've got here is the reusable water bottle, but you know what? You don't necessarily have to go out and buy an expensive water bottle to use. You can just buy your first bottle of water and then top it up again. And that's reusing and will lead to you reducing the amount of plastics that you're using. And now I'm going to spend a bit of time talking about recycling. And so the next thing that you can do is you can think about recycling your plastics. And you might be familiar with these triangle symbols with the numbers in. And what that tells you is that, the fact that there is a triangle tells you that it is a material that can be recycled, not necessarily one that is recycled, but it can be recycled. And the number inside the triangle tells you what the material is. And I'm going to concentrate particularly on number 1, polyethylene terephthalate, but also I'll be mentioning polypropylene, number 5, and probably high density polyethylene, number 2. So in some places, and these are actually separated, people collect them separately in the first place. But in most places, all of your plastics are just dumped into the recycling bin together with no separation at home. So this is polyethylene terephthalate, and one of the great things about it, well, there's several great things about it. It's a wonderful material. It can be used for a whole variety of different things. It can be water bottles, it can be bags. Polyester, when you talk about polyester cloth, is polyethylene terephthalate as well. So it has this huge range of uses. So it's a great material. But also one of the things that's also great about it is that it is a material that is relatively easy to recycle. And we're going to look a little bit now about how that recycling happens. For those that are doing A-level, I should point out this is a polyester, and you can see that it has the ester link in it, and that will become important in a minute. So there you go, there's your plastics recycling, just emptied out of the bag, all sorts of plastics mixed together. But what I want you to look at is the drinks bottle, which has the bottle itself is made from PET, polyethylene terephthalate, whereas the top will often be made of something like polypropylene or high density polyethylene. And so you now have these two different plastics together, even in the one product, let alone in the collection of all of the waste. and you have a separation problem because you need to separate these plastics in order to be able to recycle them. And that's what happens when your plastics arrive at the recycling centre. The first level of separation is actually, you know, a physical manual separation where people see what's going past them on the conveyor belt and separate them off to as much as they can. Now we need to take a little detour and talk about the electromagnetic spectrum. And so you'll all be aware that light has a range of colors in it. You know, when we see a rainbow, we see the visible spectrum split into, you know, it's red and orange, yellow, green, blue, indigo, violet. We see the spectrum in the rainbow. And of course, those colors are different wavelengths of light. But the wavelengths of light go beyond the range at which we can see. And if you go down past the indigo and violet, you get into the ultraviolet region and eventually to X-rays. And X-rays are, of course, the kinds of radiation that we use to be able to X-ray us and see when we've broken a rib or something. If we move to the other side, and so beyond red, we see the infrared frequencies. And so those are the frequencies that you use for something like your television remote control, and so on. It goes to microwaves, and it's microwaves that carry your telephone signals, and then eventually radio waves, which carry the radio and television signals. So let's come back to the infrared. So here we see, and it looks quite complicated. The reason it looks complicated is because it's got 5 polymers represented on it. So if we scan the infrared range of wavelengths, so from about 1,000 nanometers to about 2,500 nanometers, we get these graphs. And what these graphs are telling us is how much of the infrared are being absorbed by the various different polymers. And what you can see, the way they're overlapped is designed to show you this, is actually there are places where they absorb differently to each other. So for instance, if we look at this, the region about 1,200 nanometers, PET doesn't absorb at all, but the high density polyethylene and polypropylene is not on here, but the high density polyethylene and the polypropylene absorb very similarly, do absorb there. And so if we can read off where the particular plastics are absorbing, we can use it as a method of separation, and it is. And so you can see in the picture on the top right hand side a schematic of that, in which you scan the mixed waste, you detect it by infrared detection, and then actually what they do is they use air nozzles to blow selectively the different elements to sort them. Another way of separating plastics is like this. And so what happens is that all of your bottles and whatever they are get shredded down into fine flakes of plastic. And so it's a bit of a myth. People say, oh, you have to take the lid off your bottle when you recycle it because they're different polymers. That's a bit of a myth, because in most places shredding happens, and so you have this mixed shred of plastics, and then the separation comes after that. And it comes really, really simply. So you can see the picture of the glass, and what you can see here is that PET is more dense than water, whereas high density polyethylene and polypropylene are less, in spite of the name, are less dense than water. And so they float to the top and the PET sinks to the bottom. And then you just have these water separators where the plastics are separated according to their density against that of the density of water. And so you end up separating your plastics, and then eventually you're getting them so that you have the separate pure streams so that you can actually then do the recycling. And then I said we'd come back to the esters. And so the final thing that happens is, particularly if the PET is going to be used for some very high value purpose, like making it a bottle again, where it really matters that it is super, super clean. What often is done is a thing called a chemical peel. And so that's to do some chemical reactions. And the reaction is ester hydrolysis. So esters react with water to give acids plus alcohols. And the way it's done in recycling of PET is like this. So first of all, you need to catalyze the reaction. If you think about it, you can't have a water bottle that, if you fill it with water, it dissolves. And so what is required for the ester hydrolysis to occur is some catalyst, and it is stimulated by adding strong base, sodium hydroxide. And what that actually gives us is the sodium salt of the terephthalic acid, so disodium terephthalate, and the ethylene glycol as the alcohol. Then what happens is you then give it an acidic wash with water, and that gives the final hydrolysis to the terephthalic acid and sodium sulfate, which you can then recycle round itself. So you have these chemical peels that react off the very thin top layer of the bottle to clean it, the plastic to clean it. Now, in fact, this is also an area of very active research, because what many of us are trying to do is to say, well, actually, maybe the best thing to do is, rather than try to clean up the plastic and then recycle the plastic, and in so doing, we know we always get a bit of degradation of the plastic. Why not try to change the polymer back into monomers, and then use those monomers to remake the plastic from scratch? And there are three technologies that are being used here. So there's the hydrolysis, so similar to what we've just seen in the peel, but designed to dissolve all of the plastic. Methanolysis, so that's using methanol to make a methyl ester of the terephthalic acid, which can then be used to make the polymer again. Or the other one is glycolysis, which is to use ethylene glycol, which is, of course, the alcohol that from which the polymer is made itself, and then use that to make the starting material for your polymer. And there's a lot of research in this area, and I wouldn't be at all surprised if in the next few years we start to see some commercial processes. So my final R of this bit is responsible disposal. And again, we're back to something that you can do. And so very, very simply, what you can do is take your litter home with you. If you don't take your litter home with you, at least put it in a bin where it will be collected from, so that it can be disposed of responsibly. Another thing that you can do, another thing that lots of people can do, which is to take part in a plastics litter picking on, a beach or a canal side or some such place. There are lots of organisations that regularly organise these, and it is a great way to, well, actually have a bit of a fun time out, but also to clear up the beaches and get the plastics responsibly disposed of. So at the Royal Society of Chemistry, we've been looking into how we can have more sustainable plastics, and some of which I've already told you about, and that is to understand the impacts that different plastics have throughout their life cycles, and we've talked a bit about that today. The other one is to have closed loop plastic recycling. So that's really having a system where we ensure that all plastics that get used get back into the recycling system. Another is to understand and control plastic degradation. So to be able to understand plastics and how they behave in the environment so that they biodegrade. And then the final thing that I'm going to give you one last little look at, one last R, which is to develop new plastics that are more sustainable than the ones that we currently have. And so my final R is to replace. And this is something, again, which is a highly active area of research. Many of us are interested in using the polymers that are naturally part of biomass, so trees and plants, that they're really strong trees, again, don't dissolve whenever it rains. And so the structural polymers that give wood its strength are these. They're cellulose, which is a glucose polymer. So you get long strings of glucose, which are then bonded to each other by things called hydrogen bonds. Again, some of you will learn about those. And then those chains bonded together make sheets, and those sheets stack up in piles to give a very strong, durable material. At the bottom, you can see a wonderful material called lignin. And lignin, look at all those lovely aromatic groups on the lignin there. And unfortunately, cellulose is already used for lots of different things. There are cellulose films, cotton is cellulose. Lignin, in spite of it being such a potentially wonderful material, still has yet to find its uses. And there's a whole area of research in trying to make something useful from lignin. In fact, there's a saying in biomass chemistry which says you can make anything from lignin, it's such a beautiful molecule, except money. And so what we need to do is to find ways which are commercially viable to turn lignin into useful replacements for the plastics that we use today. So here's the synthetic challenge, and for those of you that decide to go on and study and maybe even research chemistry, this is the challenge that I have for you. And the first is that what we need to do is we need to make materials from renewable resources that we currently have available today. So sometimes we actually want the material to be the actual material. Other times, though, we're not that bothered about what the material is. What we want it to have is a property that is useful to us. So, we don't mind whether our drinks bottle is made from PET or whether it's made from something else. And so we want to make new materials that match the properties of currently available materials from biomass sources. And finally, of course, the interesting thing that will happen is as we do all the research trying to make these materials, we will discover new materials that have new properties that we don't currently have available to us. And they will turn out to be interesting and useful, and we will make use of those new materials. And of course, all of the processes to make these materials must be sustainable themselves. So with that, I would just like to say thank you. Don't forget to make your plastic promise. You can do it at the website here. And I shall stop sharing and see if you have any questions.
Thank you so much, Tom. That was fantastic. I learned so much. 30 different elements in our mobile phones. That's incredible. Yeah. And also, I think I learned a new material, indium tin oxide. That is the material used in our swipe screens, which is incredible. And it's unbelievable that for some of us it was so insignificant, and then now it's serious risk. That's really crazy. So just what I wanted to ask you was, you mentioned the products. So many of our plastics, so many products of plastic in these days, it was designed to be durable and stable. It's difficult to break down on purpose. So it is a remarkable material. But how can we value it more, as in the general public and the industry really put value in plastics?
So I think it's one of those kind of strange problems. You know, why have plastics become so prevalent in our society? And it's because they're so useful, which is great, but also it's because they are generally cheap. And so when I think about, you know, that 30-year-old cutlery tray in my drawer, you know, I have no idea how little it costs, but it would literally have been pennies. And what that often means is, because things are cheap, we don't value them. And so, you know, I will know people that bought a drawer tidy at the same time that I did, and have had 10 since, because they fancied a different color, or they did, you know. And so we have to value the material property, not the price of the material. And yeah, there are uses that actually I want a highly durable material that has been designed to in no way degrade. And of course, when I then dispose of it, I have to dispose of it like it's a very valuable thing. You know, I have to take it to a recycling center where it will go to the right kind of recycling and be used again to make whatever it's next. Then, of course, there are the uses of plastics, which are, you know, when I see in front, I've got actually, I think this, now I touch it, it might be cellulose. So that's good. But, you know, I have, you know, wrapping to something that's just been posted to me, you know, a cheap biro, and, you know, and there are many things that what we would want to do is, if we are to continue using them, and we then want to make them out of degradable things, then we want to decide almost beforehand, we want to say, the first question is the thing that I'm making something that I want people to value, even though it's cheap? And is the thing that I'm making something that, you know, I just have to accept nobody's going to value that? The first lot we need to make out of a durable, easily recycled material. The second lot we want to avoid, actually, if we don't need that thing, but if we do actually need to use it, then to make that maybe out of a biodegradable plastic. So when it does end up in landfill somewhere, it will biodegrade away.
Thanks, Tom. There is a question from Philip. It says, I presume the 5 Rs were arranged in a hierarchy from refuse to responsible disposal. Where would you replace fit in?
So I think, you know, I think I might put my sixth my sixth one in. But, you know, I mean, all of these things are just, they're simple tools that enable us to remember. Mm-hmm. You know, so the 5 Rs, you know, like I say, when I first came across it, it was the 3 Rs, because we didn't have refuse and we didn't have responsible in there. But, you know, and whatever people can do to help them remember, here's what I can do in order to improve the situation, then, you know, if there were 20 Rs, we would forget them all, but 5 or 6, fine.
Thanks, Tom. Emer is asking, why do you think we still haven't fully been committed to replacing the plastics now to the alternatives that you talked about?
So replacing with some of the alternatives that I talked about at the end, the reason we can't do it is because we don't yet know how to do it well. And again, in a kind of commercially viable way. And you know, what you've got to remember is many of the things we're replacing are incredibly cheap. You know, they're almost without cost, they're so cheap. And so therefore, if you can't replace them with something which is terribly expensive, because nobody will buy it. And so we have to work that out, and we have to work out the technology for doing that. The biggest problem with biomass at the moment is actually the very first step in the series of reactions, which is the, you know, dissolving and separating the wood into its component parts in the first place. And once we crack that, then I think it'll take off.
And always Emer is adding actually another comment, say, is this a growing sector that needs more people getting into it?
Yes, absolutely it is. You know, it's grown a lot in the last few years, but there's there's still so much work to be done. You know, it's a real, you know, speaking to you as, you know, school students, you know, it really is an area where if you want to make a real difference to the world, you can make a real difference to the world by studying the chemistry that you need to learn to be able to do this, and then being the people who make the materials that then go on to be the new materials. That's absolutely a challenge for people of your age.
Tom, do you know how many times a plastic bottle could be recycled before the quality decreases to the point that it can no longer be used?
So that's very hard to judge, because of course what happens is that you don't have plastic bottles of the same age going through the recycling system together. And so you have some plastic bottles that maybe they're on their first use, other plastic bottles have been recycled several times already in the mix. But you know, it's why we're interested, those of us that are interested in the depolymerization route are interested in it. But there is a degradation. So it's called mechanical recycling. Basically what we do is, you know, having bashed them to pieces and separated them, they get melted back together. And every time you do that, you get some degradation of the polymer chain length. And so the reason we're interested in the chemical recycling is you can say, do you know what, that doesn't matter. Because what we're going to do is we're going to take all of this back to the monomer and start again. And yeah, and so I don't know the answer to your question, but I think the answer to your question isn't really known, if you see what I mean, because it's too complicated.
Do you think with all the developments going on that one day chemists might deliver a plastic bottle that can be reincarnated forever?
I think that's what taking it back to the monomer will do. Yes, so that is essentially the way of doing that. You know, it's the idea that you might have a bottle that, you know, you can recycle the plastic. You know, I mean, it can be a bit, once you're in the recycling center, it doesn't matter if the thing in the recycling center is complicated. What matters is what goes in the door and comes out the door.
There are two questions that are very similar. One is from Sandra and the other one is from Emer, and is related to what sort of advice you would give to students that have a great interest in green chemistry, sustainable chemistry, so what they should do to take a career in this sector.
So the wonderful thing about chemistry is that it does give you a pathway to a career. You know, it is an academic subject, but it is also a subject which is vocational and will lead to jobs. And so if it's the right thing for you, then, you know, studying chemistry at university and carrying on through that route. But of course, there are other routes. You know, you don't have to necessarily take an entirely academic route. There are lots and lots of chemistry apprenticeships available now, and so there are other routes into a chemistry degree, you know, into a chemistry career. And actually, there was a study that the RSC issued earlier, you know, a month or so ago, and it showed that there are 275,000 people who use chemistry in their job. Yeah, that's incredible, isn't it? That's a huge group of people. So there are wonderful careers. You know, you don't have to end up being a professor. There are lots and lots of careers that you can take up, which will still be chemistry. So that's not even the people who studied chemistry and then used it to go into something else, which of course you can do. But the ones that stay, basically at some point in their job, they still use chemistry. Nearly 300,000. So that's, you know, a lot of opportunities available to you.
Tom, Emer, who's doing our A-level, says, how optimistic are you that we will eliminate plastics within the next 20 years? Do you think we ever will?
Well, no, I don't. So I don't think we will eliminate plastics in the next 20 years. What I think we might do, which is what I think is the right thing to do, is to eliminate the plastic products that we don't need, but that's not all plastic products. Plastic is wonderful material that is extremely useful. What I think we need to do is to work, obviously we do need to get rid of the things that we don't need and get rid of them. But what we do need to then think about is how we make the remaining plastics easy to recycle. So some of that is about chemistry, some of it is about making polymers that are easy to recycle, both physically and chemically, like I just talked about. But it's also about the product design. And so if your mobile phone had been designed with recycling in mind, it would be different to how it, well, on the inside, it would be different to how it is now. And so nobody thought about how are we going to recycle this phone when it's finished with use? What they thought about was, how can I make it in a pretty box? How can I make it look more appealing than the other phone? They thought about those things. And so designers need to think about not just the material, but the whole product. And how can I make the product easier to take apart? Because the first step of recycling a complicated product is to be able to separate it and take it back to its component parts. And I think there's a realistic possibility in 20 years' time that we will have better, more recyclable materials and better, more recyclable products, as well as having got rid of the material, got rid of the products that we just, why on earth does anybody want a plug-in air freshener? Try cleaning your house.
Do we still have time?
Another one?
Yes, just the last one probably before we wrap up. You mentioned 3 methodologies when you were talking about recycling plastic. So I'd like to know at what stage are we with these 3 methodologies, and if there are companies already investing in this service.
So do you mean the reactions, the chemical reactions?
Yes, when you were mentioning, yes.
So yes, there are companies investing in it and looking at it very, very closely. All 3 of them have the potential to make processes. My guess, I think the hydrolysis might be the less successful one. I think more likely the methanolysis or the glycolysis. The thing about the glycolysis is that the product that you get from that glycolysis reaction is actually the monomer which most companies that make PET make it from. And so it's really very direct. You just take it back to its starting materials, do the reaction again. You don't have to do anything in between to take it from the thing that we depolymerized it to the thing that we want to use to make it. And there's a kind of rule of thumb in green and sustainable chemistry, which is the fewer process steps you have, the more sustainable your process is likely to be. And so anything that reduces the number of operations is good, but also in terms of the chemical engineering, on the whole, the more process steps you have, the more expensive it is to do it. So the 2 go hand in hand.
Great. I think that's a great note to end on. So thank you so much, Professor Welton. I really appreciate your time in doing this with us today. And thank you to everyone, all of our participants, for taking part in attending. It was great. Remember to add your plastic promise and make sure you check out our website for your International Certificate of Attendance for Eco Schools, and check out our other webinars through the Eco Schools Facebook page. So thank you very much, everyone. Take care. Bye-bye.
Bye-bye, everyone.
Bye.
Bye.